Well, we were explaining about the chemical treatment of mine wastewater in general, and we are discussing about the empiric property of most of these metal hydroxides and sulfides. We have also observed that that in situations like where in a solution all these metal hydroxides and sulfides generally show a particular preference of pH when their precipitation rate is high, precipitation rate is highest for them, and also to observe that they show a minimum solubility in water at a particular pH. This particular property of this metal hydroxides, metallic hydroxides and sulfides are greatly used in chemical treatment. I have also discussed the procedure essentially is like this. I have given you a particular idea about how this the plants can be designed with that in mind. Let me explain you a little bit on this. Say here, if you just observe this amphoteric property in a graphical form, this is how it looks like. It's a concentration of dissolved metal, and if you observe this in terms of pH here, we also consider the pH 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and say 14. So here, okay, so what we observe, the pH in which the water can remain. See here, what is important here is this to observe here is, say at about 11 pH, this is the AGS, it has the this is the AGS, this is silver sulfide. So you can find out here this this particularly has a minimum solubility here. So what we are trying to do is, suppose if you want to precipitate silver sulfide here, what you try to do is just to maintain the pH at about 11, pH of the solution to be kept at about 11, so that the maximum solubility, the minimum solubility takes place, and most of the material which are in the saturated condition would come out of the solution of water and precipitate. Similarly, all this if you just observe this for particularly for other sulfides, if you just observe about 11, at about 11 these other sulfides, if you just observe this, that they would also come down like this. Then this is how this is how the plot should be. Say this is one is cadmium CDS, cadmium sulfide. This is for the zinc sulfide. This is for COS, cobalt. This is for CDS. This is for PBS, lead sulfide. So here you can see this particularly like this. We observe these plots. If you just try to observe this is for the sulfides. This is for the sulfides that we observe a similar kind of situation. So what is the plant specification is, if you are just trying to, if you are interested in separating out, if you are interested in precipitating, say the particularly if you are these salts, particularly AGS, PBS, CDS, zinc sulfide, and say COS, cobalt sulfides, you have to maintain the pH at about at open atmosphere at STP. Remember, this is at STP, that is at STP. If you maintain a pH between, say here as you can see 10.5 to say 11.5, you can selectively precipitate. You can precipitate all these sulfides from the water. You can precipitate all this. This is what is called the amphoteric property. That is what I explained, that almost all zinc sulfides and almost all metal hydroxides and metal sulfides show a minimum solubility, at a particular pH. So this helps us, in preparing for the plant structure, how the plant has to be designed so as to selectively precipitate some of these sulfides and hydroxides. Similarly, this one case for hydroxides, if you just observe, for hydroxides, if you this is an amphoteric property. Similarly for hydroxides, if you just observe this for hydroxides, this is how it would be looking like. So this can be thought of as something like this. Say in here, if you just observe here, say at about, say between 8 pH, 8 and say about 12, if you just see 12, 8, 9, 10, 11, 12, if you just observe this, almost all metal hydroxide, copper metal hydroxides, almost all metal hydroxides would begin to precipitate here. So this is how it would be. So some of them are going out actually just because of my drawing, but you can see here. So this is where the minimum solubility is. This is where the minimal solubility is. This is the concentration of dissolved metal hydroxides. Concentration of dissolved metal hydroxides. All this you can see if you just maintain a pH, manipulate a pH. So here this one can be, all this can be precipitated selectively. If you want to do it selectively, you can selectively do so. You can selectively do so by targeting the minimum solubility zone. So you see, if you are targeting the minimum solubility zone, you can selectively precipitate, say a particularly, say this is one is for CdOH2, this is for AgOH, this is for CuOH2, this is for zinc OH2, like this. This is for, right? All we are trying to do here is just to, as I was discussing in the last class, you could see that I have talked about the streams by which, if you can maintain a certain pH, for different metal hydroxides, we can selectively precipitate them. This is possible because of the amphoteric property of these metal sulfides and metal hydroxides. So the stage here is, if you just observe it like this, what we generally try to do is, say this is if you just see the plant here, this is what is in a pump like this, which would be finally discharging onto, say this, and similarly there would be another term. You can see here, this is what is, these are two pumping arrangements. These are two pumping arrangements. This is where the water, where the water, influent water is being discharged here, influent water is entering here, influent water. Now selectively, this is influent water, this is this is a alkaline buffer, this is an acidic buffer. This is an alkaline buffer, this is an acidic buffer. So you can see this, you would, and here would be 1 pH meter. So here would be 1 pH meter. So depending on say this, depending on the type of pH that we would require, we would use either the acid or the alkaline so as to get suitable pH, so that at that pH a certain the particular chemical that has an attention, that we have an attention. Suppose if we have a waste, particularly say if you consider say metal mining waste, say considering metal mining, say metal mining waste, the three typical kind of wastes we have. This is lead, cadmium and chromium and copper, 4. Lead, cadmium, copper and chromium. See this 4 you can see, if you are targeting copper, you would run into a stream where you will try to maintain the pH say between 9 to 10, say about 8.5. So here in this here you would maintain the pH at 8.5, so that most of the copper hydroxide precipitates. So if their copper hydroxide is precipitating, what essentially is happening is the concentration of metal is going down in the solution. All right. So this is what is known as the lime treatment. This is what is the famous lime treatment that we generally do in most of this environmental industry. Lime treatment is a very standard method of treatment. So this is a very effective method of treatment for different kinds of metallic ions. So it essentially you are trying to do is at standard temperature pressure, we are trying to see the solubility. We are trying to see the solubility, and particularly the minimum solubility at that pH where it would begin to come out of the water and it would begin to precipitate. So this is what, as a result of this, we would like to more and more get into they selectively precipitate different kind of sulfides and hydroxides. Now here, as you can see, at times when the acidity would increase, say we are getting acidity towards say from 7, 6, 5, 4, 3, 2 like this, and if you want to increase it to say we want to increase it to 9, 8 or 9, in such cases we have to use more alkali on this. So you would use the alkaline buffer, and in the same case when you require to reduce it, say from 11 to 8 or 11 to 8.5 or 6.5 or 7, or say about that much. So in such cases we have to use some acidic acidic buffer, so that combining these two, continuously monitoring that, we can separate out a number of metal hydroxides and sulfides. This is famously known as the lime precipitation technique, which is generally used is, so to say, is very simple, and is a very very cheap also as a method of treatment. It certainly has its disadvantages and advantages, but considering that also we find a great use of this treatment method. Okay. So here we would just try to see. So as you can see, in most cases the binding reactions is basically the precipitation of most of these metallic hydroxides and sulfides. So there are certain advantages and disadvantages connected to this. This is one is the advantages that we can generally observe in cases like this, is that neutralization is reduction of specific metal hydroxides and sulfides, increase in pH helps in reducing a number of things as well, removal of heavy metals that it takes place. Cheap and easy to maintain. Cheap and easy to maintain, quite effective in the absence of other treatment methods. In the absence of other treatment methods. Disadvantages that you can generally observe in this kind of the lime precipitation technique. The number one is that scaling hydroxides render it ineffective after a period of 1 to 2 months. Armouring of lime chips, armouring of limestone chips kept to increase alkalinity. Is a problem. This reduces armouring, ARMOURING, armouring of limestone chips kept to increase alkalinity is a problem. This reduces the surface area of exposure, of the limestone particles, and thereby rendering it ineffective. Frequent maintenance is a problem. Frequent maintenance for descaling. Frequent maintenance is a problem. Descaling. Say another important part is effectivity. Reduces with time. Effectivity reduces with time. So, okay. Now, this is effectivity reduces with time. So, you can see this, this is one big important method for secondary treatment that we have observed, and so you can see that this is one treatment method that has a great application. Okay, This is about the lime chemical precipitation technique. In any question you have, anything that is not understood, say, let me again explain you this, that amphoteric property suggests that all metal hydroxides and metal sulfides have minimum solubility at a particular pH, So at that point their solubility becomes minimum. So for our plant design specification, we like to keep the water into those particular minimum pH, in those particular pH values, so that the solubility of the metal hydroxides in the solution of water becomes minimum at that temperature and pressure, at STP that we consider. And so if we maintain that way, we can selectively and we can grossly precipitate a number of metal hydroxides and sulfides from the water. So as a result of that, the metallic cations in the water, concentration of cations in the water begin to decrease, and as a result of that, water begins to be more purified. Okay, but at the same time, it is also, as I have said, hardness increases. The another important hardness of water increases. Hardness of water, the effluent water, finally the effluent water, as we was discussing, the effluent water finally would be the effluent water that I said, in a different vessels through which this water would pass, would essentially, so you can see this effluent, we can say this ferric hydroxide FeOH3 being deposited here, then you can find out zinc here. So selectively maintaining that, you can precipitate a number of these substances, but this effluent, essentially this influent, in most cases of this nature, if it is the effluent pH may be say 4 to 6 pH, whatever this effluent pH become 8 to 10 or say even 8 to 11 pH. So you can see this is as a result of that, the alkalinity, increasing in alkalinity, also increases a certain kind of hardness in the water, which makes the water otherwise not usable. We have to deal with this in a separate way. We have to find out methods by which, say, by either by heating or by any other process, to reduce the hardness to a certain extent. So this is, if you just observe this, this is one very important technique of this. Another kind of tertiary treatment, we will not find time to discuss all the method of tertiary technique, tertiary treatment methods. Tertiary treatment methods. We just observe these tertiary treatment methods. Here we could talk about chemical reduction, oxidation, redox, based treatment. See, as you know, in any kind of chemical equation, if something gets reduced, something gets oxidized. So essentially, particularly that kind of feature always exists. So you can see is that we can observe, particularly what we generally observe here is, say, we would particularly this kind of redox techniques, this kind of redox treatment is suitable, particularly suitable for immobilization. This is the word immobilization of say immobilization of species of metals like immobilization of species of metals like chromium, then cyanides, and chromium, okay, chromium, then you can see arsenic, chromium and cyanides for immobilization of species of metals like arsenic, chromium, and also decomposition of these cyanides. The cyanides are extremely toxic. So are this arsenic and chromium. But remember one thing here. What is the property that we see is we generally is the hexavalent chromium, that is chromium 6, we call it hexavalent chromium. Hexavalent chromium is extremely toxic. This is called chromium 6. This chromium 6 is extremely toxic, but not the trivalent chromium. This is Cr3. See, this is what is called species. Which have, when the same metallic ions would undergo the changes in the valency. They will have different valencies. Like that if iron, ferrous ion and ferric ion, the valencies are different. So this this is what is this the valency, the hexavalent chromium. Hexavalent chromium is toxic, but not the trivalent chromium. So what we try to do is here, we do not want to reduce or we do not want to precipitate chromium here. We may like to render it from hexavalent chromium to convert into trivalent chromium. So that if we can make it trivalent chromium, it would be largely immobilized. That is, it will not move from one place to another. This is number one. And secondly, in any kind of say digestive tract or any other passages through which it will pass, it will not be reactive. It would remain as it is. It would completely pass. Neither it would be absorbed in the physical system, neither it would be form any compound with any other substances. So it would just merely go into the food passage, through the food passage and through the excretory channels. It will just simply come out of the body, but it will not react. But not that, particularly that property is not good for hexavalent chromium. Hexavalent chromium is highly adsorbable. It will be adsorbed in the different streams of the body during the movement through the digestive canals. So here what we try to do is the water containing hexavalent chromium will be reduced to trivalent chromium. With the idea this hexavalent chromium is particularly where chromium is used. Chromium is used for steel finish. In steel, chromium is used. Chromium is used in a number of polishing industries where there are metal polishes are required. So the fine metal finishes that you see generally in all say industrial complexes and things like that are mostly layered thickly by chromium. So the chromium is a very highly usable material, is highly used, but as such what we try to do is we generally would like to reduce the trivalent chromium, reduce the hexavalent chromium into a trivalent chromium. So what we generally try to do is we run sulfur dioxide in a controlled manner. This is sulfur dioxide. The sulfur dioxide, the reactions are running sulfur dioxide, run sulfur dioxide. You just say run sulfur dioxide, run SO2 in the stream of wastewater, What we are trying to do is, we are this 3SO2 plus 3H2O, this is combining with water. As you can know, this is 3H2SO3 it will make. This H2SO3 would combine with then this 2H2SO3. This the next stage of reaction is there's the reactions that would be forming in 3SO2 plus 3H2O forming say sulfurous acid number 1. This equation, as you can see here, this would be dealing with chromium oxide. You can see this, the valency is hexavalent, chromium 6 here, hexavalent chromium. This one would be dealing with 3H2SO3 to form Cr2SO4 plus 3H2O plus 3H2O. You can see this, this would be forming 3H2O. So this one you can see now, particularly this chromium, hexavalent chromium, has been converted into a trivalent chromium. So nothing actually is getting precipitated, only the conversion from hexavalent chromium to trivalent chromium is taking place. It is within the solution itself, nothing is coming out of the solution, but simply because we have been able to convert this chromium, hexavalent chromium, into a trivalent chromium, our purpose is solved. So you can see here this hexavalent chromium is becoming reduced. Okay. So as a result of this, you can see this is the reaction, which is a typical redox reaction that is generally done to neutralize the highly reactive chromium 6 into non-reactive and stable chromium 3. Okay. This is another important area for this kind of analysis is where we use generally, say the cyanides. Another is the cyanides that we generally use, that is the destruction of cyanide, say the destruction of cyanide. Destruction of cyanide. The destruction of cyanide. How we do the destruction of cyanide? What we generally find out is, using alkaline chlorination. Using alkaline chlorination, we would be destruction of cyanide takes place using alkaline chlorination. Alkaline chlorination is this. This is, say, NaCN. This can be NaCN. This can be any other substances like sodium cyanide. This can be KCN also. This can be KCN. Then it can be MgCN2, right? all these substances, this should be reacted is alkaline chlorination. This is a chlorine, the gas of chlorine, and the chlorinated alkaline solution, chlorinated alkaline solution, that is NaOH, chlorinated alkaline solution. You can see this chlorinated alkaline solution, chlorinated alkaline solution, leading to NaCNO in the first stage, 2 NaCl. This is pure simple sodium chloride and H2O. So we are using this one. But you can see, you can very well write for other substances also. You can see KCNO, then there's KCl like this. You can find out, and H2O. This is the reactions can take place like this. KCNO, NaCl, like this. H2O would form. This one would be then 2 NaCNO, again reacting with chlorinated alkaline solution, 4 NaOH would give rise to 2 CO2 plus N2 plus 6 NaCl plus 2 H2O. So here you can see this finally, this C, this N, this C and this N finally being destructed into carbon dioxide and nitrogen. This is also another kind of redox reaction where the destruction of these cyanides take place. So we can think of these redox reactions. We can see the usual experimental procedure is to measure cyanide before being treated with chlorine and sodium hydroxide, and finally the effluent, which is influent and effluent, the concentration of cyanides would be measured to find out how this is actually, what are the typical the breakage into carbon dioxide and nitrogen. And so finally the water that you would generally find out if you just stir the water quite a while, this nitrogen does not remain, nitrogen is not a much soluble material in water, so it would leave the water, so would be the carbon dioxide at STP. And so what we find out is sodium chloride and 2H2O. So the water being almost completely purified by from cyanides. Okay. So this is a typical tertiary treatment. This is a typical tertiary treatment that are generally found a good use. This is also, this can be this, that there are different kind of other substances that are generally dealt with is the mercury, lead, silver, the chlorinated organics, like PCB, and also unsaturated hydrocarbons. Unsaturated hydrocarbons means, which is the bonding has not been saturated yet. It can be further saturated. a saturated hydrocarbon and a unsaturated hydrocarbon is, the difference is the unsaturated hydrocarbon would continuously try to link more and more carbon and hydrogen bonding. So, this would continuously develop. This is known as unsaturated hydrocarbons. When the saturated hydrocarbons are the hydrocarbons which are not generally add further into that. Say, mostly the fat can continuously combine. So, this would be known as unsaturated hydrocarbons. Similarly, the carbohydrates are essentially saturated hydrocarbons. They will not attach anything else with the bonding. So, the carbohydrates, the fix is there, so it will continuously remain in that. So, here it is. So, this is what is, you can see that in particularly when you are targeting a particular metal, when you are targeting, say you are targeting mercury, you have in a particular source of industrial water or any other water for drinking water purposes, you have high dose of mercury. This mercury may not be replaced, cannot be simply taken out by, say, a lime precipitation technique. You have to have a technique like redox reactions, where these things should be separately can be handled. So, this is where when there is a particularly very specific pollutants to be reduced, specific pollutants to be eliminated from the wastewater, we would go for tertiary treatment. And one of the very famous tertiary methods of tertiary treatment is redox reactions. There are few more, there are many more actually, there are many more, but this just gives you the basic of where and how these techniques can be used. Okay. So, having gone from this, here we have mostly discussed about this treatment of wastewater. I just deal with highly, say, metal enriched wastewater, application of wetland treatment and biotechnology. Application of wetland treatment and biotechnology. Application of wetland treatment and biotechnology. This is the emerging area. These are the emerging area of metal enriched wastewater. We have discussed so far, say, this treatment which are chemical precipitation technique. I have also said during the disadvantage that it also creates a certain amount of alkalinity. It also creates, say, different hydroxide sludges. See this, in particularly this lime precipitation technique, you see you are producing calcium hydroxides. So, that is also another kind of waste that has to be disposed of, isn't it? So, calcium hydroxide, even if it is not very harmful, but you have to dispose it. This can be an irritant. I mean, even if it is not harmful, it can be an irritant in the process, in the technology process. It can be, if it is remaining there in the process, it would lead to disruptions in the methods. So, here here we will be discussing about some of those wetland treatment methods and the use of biotechnology in this particular area. We will just briefly discuss about the principles of use. Okay, wetland treatment. I will discuss with this. Wetland treatment are generally split into aerobic treatment, aerobic wetland, anoxic wetland, and we can further differentiate this into anaerobic wetland. Okay. Aerobic wetland treatment, you can see this say sufficient air, sunlight, air and sunlight and exposure. Here this would be sufficient sunlight, but insufficient air and exposure. Here in such cases, in anaerobic wetland, we have both deficient air, sunlight and exposure. So this is what is known as the anoxic aerobic wetland, anoxic wetland, anaerobic wetland. We can see this is the structure, here to see this. What is important here is, in all these cases, this is particularly the treatment here is, it says this is the reactions here, it is bacterially aided. But this one is bacterially aided and controlled. Bacterially aided plus controlled. Okay, the first one is bacterially aided, anaerobic wetland, bacterially aided, but it's not controlled by bacteria. The next one is bacterially aided plus controlled. I mean, in an equal measure. It's not fully controlled by bacteria, neither it is fully aided, it is aided by bacteria and not fully controlled by bacteria. But in anaerobic wetland treatment, is the whole process, the condition of this, the reactants, the reaction process, the rate of reaction, the equilibrium of the reactions, all these are actually bacterially controlled. Separate, different distinct species of bacteria actually aid these processes. Distinct species of bacteria aid these processes. Remember, the aerobic bacteria will not survive in anaerobic environment. Neither the anaerobic bacteria would survive in aerobic environment, and there is a tremendous competition between these two groups in a natural environment. So you can see this, under a situation like this, we would consider this wetland treatment as this. Under this, we will discuss some of the parts of wetland treatment. See, one important particularly of this kind of treatment method is the wetland where applicable. Where applicable. Number one, this wetland treatment needs large area. What happens is, I will explain you. We say it needs a large area. As a large area, this is about the area where the width would be width of the wetland, width and length of the wetland will be more than 500 to 1000 times that of depth. That of depth. The depth of the where applicable needs large area is the rate of reaction. There's another important consideration about this wetland treatment is rate of reaction. Rate of reaction is very slow. Rate of reaction is very slow. So, this has to be another important thing that has to be generally kept in mind. That has to be generally because of no artificial catalysts or enzymes are used generally for this purpose, this wetland treatment. These are all naturally aided process. The naturally aided process of sunlight, wind, all this aiding to this particular reaction. So, here we generally this particularly in such situation only this should be used where you can wait, and you can wait, and not only that, you can also expand the operation over a large area, so that even if small reactions takes place, overall it becomes large. Okay, I'll come back to this in the next lecture about this more. Okay. Well, we start this class, here, you would be discussing about the wetland treatment and some biotechnology applications. So, this is, this is the scheme of wetland treatment, aerobic wetland treatment, schematic scheme. What is generally done here is like this. If you just observe a wetland treatment system, is a waste flow coming in. Say this is, as I have said, if you remember to have said, I have said this is requires a very open land, a open land like this. Here this is what would be okay. Here you see this is what is the in this influent, the wastewater that is coming. This would be discharged here, this would be discharged here, and this is where the wetland would be. Wetland would be. There are different ways to do it, different ways to design a wetland. The most common one, there are in some cases it's optional. Remember this is purely optional to have a liner at the bottom. It's not necessary that all wetlands would require a liner. If there are, if it can be, the whole thing can be insulated, so better it would be insulated. So, we have generally a liner in some cases, but as I have said, this is not mandatory. This is not mandatory. Just to, well, this is what is the waste. This is what the wastewater would be. There would be few other things here. There would be few other things here, as you can see. In some cases, we will find that some substrate, say the fine soil substrates, are also generally spread over. If it is a designed wetland, this is what is a designed wetland. We can see, find out. This is the fine grained soil. This is a fine grained soil. PVC liner, non-reactive liner, certainly non-reactive. It should not react with the wastewater. This is the fine grained soil. This is the fine grained soil. This is the fine grained soil. This fine grained soil essentially works in for one very important reason is this. This is works as a natural buffer. This also works as a natural buffer. Okay. Now here, this is the wetland. This is the water. You can see this is what is the water is. This is how it would look like. This, so the ALD is prevents ferric hydroxide armoring of limestone. This is what is an armoring. This is what is an armoring. Say, in all these particles of this limestone chips that would be present there, what would happen is the ferric hydroxide would deposit on top of this. The ferric hydroxide would deposit on top of this. As a result of this, the ferric hydroxide, as it is depositing on top of this, there would be lesser surface area exposed for the limestone to activate, lesser limestone to activate. As a result of this, here, so we would stop this ferric hydroxide deposition here. We would reduce the ferric hydroxide. This is called the armoring. Armoring of limestone. Armoring of limestone. The limestone, the chips, the limestone. So, a ferric hydroxide armoring of limestone. Ferric hydroxide armoring of limestone. ILD prevents ferric hydroxide armoring of limestone, and as the pregnant solution of say this ferric ion will be transported outside ALD without being deposited, large hydroxide deposition will take place in the principal wetland that does not contain